Yeah, so forget everything what happened today. This is about yesterday's topic, right? So edit distance. I should mention this is joint work with Karl Bringmann, Alejandro Cassis, Tomasz, who's around, and Vasileios Nakos. So let me start with the success story of approximate edit distance. And by the way, let me skip the definition of edit distances. We saw Sudata's animation yesterday. So the edit distance of two strings can be computed in quadratic time, and fine-grained complexity theory tells us this is optimal. So then, and even before this was known, people started working on approximation algorithms for edit distance. And well, I decided to include this, this list of references because it's actually pretty fun to compare the authors to the audience. Yeah, it turns out that one of the best results right now is a constant factor approximation in almost linear time by Alexander and Nozadzki. So that's actually pretty great. Like that's kind of the best you could hope for. Quite certainly late here. But if you think about it in terms of approximation algorithms, why should we settle for something like near linear time? Because for approximation algorithms, you could actually hope to get something which runs in sublinear time. Delay is kind of terrible. It's here. OK. So if we hope for sublinear time edit distance, we have to make some assumptions. First of all, we should assume that we have query access to the strings without having to force, to read the entire string. So we can access all the strings randomly in all positions. Second, we need to rely on randomization. There's no way around this in a sublinear setting. And maybe your third complaint would be, well, the problem is a little bit weird because already testing equality of two strings, like testing whether the edit distance is 0, requires you to read all strings to completion. But well, the way we typically formalize this is in terms of the gap edit distance problem, where your task is to compute an approximation in the sense that you should distinguish whether the edit distance between your given strings is at most some parameter small k versus at least some parameter big K. So distinguish the close and the far cases. Any answer, like if your strings happen to have edit distance between these thresholds, any answer is fine. And then, in fact, you could hope for truly sublinear time algorithms whenever the lower bound k is actually larger than some n to the epsilon. So, OK. So this is kind of the setting that we're going to talk about. And there has been a lot of research on this, already starting like in 2003, and then with a bunch of results following after. This last result due to Lazar, Tomasz, Robbie, who might not be around anymore, and Barna, who doesn't seem to be around, is actually optimal for the class of non-adaptive algorithms. But all of these have in common that the gap, meaning like the approximation factor, so the quotient of the upper threshold and lower one, is actually polynomial in K. So if you take a very pessimistic point of view, you would say, well, all these works are kind of compute a very inaccurate approximation factor, which is not at all comparable to what's known in the linear time regime, where you could even get to like a constant factor approximation. So then at the same time as like this last paper, actually we realized that you can indeed compute some meaningful approximation. So the gap here is subpolynomial, running this O-hat notation to hide subpolynomial factors. This is computing a subpolynomial factor approximation in time n over k plus poly k. First, in the first paper, we got it to k to the 4, and then with joining teams with Tomasz, we got it down to k squared. And this turns out to be optimal, at least in a certain regime of values k. So if you, in the low distance regime, where k is, say, at most n to the 1/3, actually the running time here is optimal. If you want to have a look at it. So OK, yeah, I'm going to talk about these two works in this presentation, mainly about the first one, and then at the end I'm going to mention something about how to optimize. And if you want to have a look at it in a picture, this is kind of the state of the art. It's a little bit annoying to read, but think about it like this. On the horizontal axis, you have the parameter k, so our guess like the edit distance of the gap parameter. On the vertical axis, you have the running time of the algorithm. Then this gray region here, it's the lower bound. Like you can never reach anything below this gray region. And the colored lines are the algorithms. For instance, this would be like all the near-linear time approximations. They actually run near-linear time, right? In the same paper I mentioned before with the non-adaptive, the optimal algorithm, they actually also prove this query upper bound. And then what I'm going to talk about is these two yellow regions. right, which actually meet the lower bound up until a certain point. Okay. Good. Now, unfortunately, I cannot start talking about the sublinear-time algorithms immediately because they're based on this algorithm due to Alexandoni, Robin Krautgammer, and Krzysztof Onak, the AKO algorithm, as I'm going to call it. And this algorithm itself is already pretty complicated. So I'm going to spend the first half of the talk just talking about the AKO algorithm. And if everything else fails, maybe you'll take away something about this algorithm. Then let's see whether we actually get something interesting from the sublinear-time stuff. And yeah, you might remember that's actually also what Tomasz mentioned at the end of his talk. So I'm maybe going to spend some more time. Good. Yeah, let me describe it in the following way. You're given two strings, x and y, and we'll build a tree on top of these strings, which has a certain branching factor b. For the sake of concreteness, let's just assume this branching factor is 2 to the root log, like a subpolynomial branching factor. In particular, it means that the depth of this tree will become root log. Now I need you to remember some notation. It's not much, but you'll manage. So for any node v in this tree, let me call the substring in x, which is like induced by the subtree below v. Let me call it x of v. So the substring of x corresponding to the node v. I would also like to define it for the y string, but we have to be a little bit more generous here. Like actually, this is called y of v in 0, because we have to consider several shifts in the string y. Like for all these shifts, we define a substring called y of v in the shift s. The reason for this is that the edit distance is a very global measure in a sense, right? You have to compare a substring not necessarily to one other substring in a string, but to to one of several possible shifts. So this is what we need. Sometimes, though, I'm going to call this entire region, which is affected by the node y of v. That's just relevant later. Now the idea is this. At every node, our goal is to compute an approximation of the edit distance from xv, string at x, to all the yvs strings. For all the shifts, I'd like to approximate the edit distance here. And it turns out you can do it using like two simple rules. Consider, for instance, a leaf node v, which really corresponds to like a single character in x. For this, you can just compute the edit distance exactly. Edit distance, again, just means you have to compare a single character. It's literally just the Hamming distance here. Okay, so yeah, by comparing all of these characters in x, the single character in x to all these characters y, you can evaluate its distance. So consider an internal node instead. For this, you need a more complicated rule. So if this node v has children v1 through vb, right? We have already computed recursively the distance estimates for these nodes, and we can combine them using this formula. It's a little bit of a mouthful, but not that complicated if you think about it. So the distance at this node is you sum over all the children. For each child, you're allowed to pick a possibly different shift si. You take the distance estimate at this node with the new shift, but you have to pay for changing the shift by paying by additionally adding its difference. And that's pretty natural if you think about it, because for any alignment of the strings which you might have in your children, you might have very different shifts. But whenever you change the shift, you also have to delete and insert characters before and after that string, which is proportional to this. You might overestimate the edit distance though, because it might happen that many of these children actually have the same shift, so you're going to pay for it several times, while actually in the edit distance you might just have to pay for it once in the beginning and once after. So it really is an edit distance approximation. But yeah, the insight is it's a pretty accurate one. So you get this kind of lemma. So the edit distance at any node v is in turn approximated up to a factor of b by this way of defining this. B, remember, was the branching factor and had this, for the sake of this talk, this form 2 to the square log n. I'm going to mention it again later, but actually there's different trade-offs possible, which actually would also lead to like a polylogarithmic approximation factor. Anyways, this is like the structural insight. Unfortunately, this didn't help so far, because if you evaluate this algorithm as it is here, it's going to take n squared time, because you have n nodes in the tree. For each node, you have to evaluate a sum, you have to take a minimum of Si of n things might be, sorry, for each node you have to compute d of v and s for s things, even if you were able to evaluate this efficiently. So you spend at least time linear at every node, meaning time n squared. But in 2 steps now we're going to make this running time be linear, or almost linear. The first one is actually a very simple observation. You need to only consider shifts up to the threshold small k. Right? Because if these thresholds would be higher, then you trivially have to have an edit distance which is more than k, so we would trivially be in the far case. That already brings down the running time to n times k, but we want to do it even faster. And there's this beautiful technique called precision sampling, which kicks in. It works like this. So actually, yeah, even if you don't care about edit distance, this is really cool. So think about the following scenario. You're at one node in the tree, and up to these shifts and this entire business, right, what you kind of want to do is you want to sum up the distance estimates from your children. So you have certain estimates of the children, you want to compute their sum. But perhaps you are actually willing to tolerate some additive error at a node, let's say beta. Then, well, that's good, because then you might also, we can tolerate some additive error also for all these children. But unfortunately, this additive error is much smaller. Right? If you tolerate additive error beta at the parent, you have to spend, well, you can only tolerate beta over b if you have b children. And well, this wouldn't really help with the algorithm because like the additive error would become very small after a few layers. So the hope is that you can assign different additive error tolerances, beta 1 through beta b, to these children, which are somewhat larger than just the naive estimate. And then this precision sampling lemma tells you that indeed you can find certain additive error tolerances. You can sample them, in fact, in like a randomized way, such that, well, this technical condition here is true. It says that the expected inverse error tolerance is bounded by 1 over beta times polylog. Okay, if you think about it, the naive one from before would have inverse beta times b. So you indeed, like you reduce from the naive solution to here from b to polylog b. Okay, does that make sense? I'm not telling you how, it's actually, it's not super complicated, but also not trivial. There's also some technical details, which I'm not going to talk about, but this really makes sense. And this is great, because let's get back to the algorithm. Oh yeah, sure.
Yeah, so when you're sampling those, you're sampling subject to the sum of the beta i's is at most beta?
Sorry, the sum of the...
Yeah, like the motivation was that...
No. Like, okay, that was the case before, right? Before you had that the sum of those was at most beta. But actually, you could do something which is way bigger, right? Maybe you could reach something where the sum maybe is beta times b. Naively, that wouldn't work at all. If you have error tolerances beta at all the children, that would blow up the additive error by a lot. But maybe you could get something for which only, like most of them are comparable to beta, but only some of them are really small. Turns out this is exactly what precision sampling does. Okay? Okay, so let's get back to the algorithm. What error can you tolerate at the root? Well, we're still in this gap problem, right? So you can tolerate an error of something like k over 10, even big K over 10. That's completely fine for us because we only have to distinguish between the upper and the lower threshold. Which means if you allow this, I've written it a little bit weirdly, right? I've written it down as like 1 over the additive error. 1 over the additive error would be like 1 over k. Now, let's go one layer down. What is the error tolerance you have there if you sample your precisions according to the previous slide? Well, then the expected inverse error becomes polylog over k. And with every other layer, it's going to increase by another polylog factor. Meaning that at the bottom, like at the leaf level, the expected inverse error tolerance is going to have the form log n to the root log n divided by k. Okay, and now remember this is one of those subpolynomial factors. So actually the numerator here is not very big. You can think of it as very, very small. This is still essentially 1 over k. But that's pretty ridiculous, right? Because it means that at all of the leaves, what you want to compute is the edit distance between 2 characters. This is 0 or 1. But you expect to have an additive error for which its inverse is expected to be 1 over k. So what we kind of expect is the error tolerance is k. It's way bigger than 0 or 1. Right? Okay? So what you can actually learn from this is that only for every kth node, the error tolerance will be between 0 and 1. And you actually have to compute something reasonable here. For all the other nodes, you can trivially report 0 or 1 or whatever. OK? And it turns out, like, you can have the analysis for the entire tree here. It turns out that this is true for every level. And the expected number of non-trivial nodes, non-trivial meaning you actually have to compute something here, in your entire tree turns out to be, well, n over k times this overhead from here. This is literally just using the expected, what's written there, like the expected number of expectation of 1 over added here. OK. So what have we achieved? Well, instead of doing something for all n nodes, you just have to consider n over k nodes. Each node takes time k, and you get a linear time, almost linear running time. OK. Good. This is the AKO algorithm. I have some time left. That's good. So let's talk about how to turn this algorithm into a sublinear time algorithm. Now, remember the running time here. It had the form number of nodes times k. And our goal is kind of to achieve a running time of the form poly k in the end. So what we want to do is we want to reduce the number of non-trivial nodes in the tree even further to poly k. OK? We're going to do this in 2 steps, using 2 insights on the edit distance problem, respectively. The first one is what we call matching nodes. So let me call a node matching if there is some special shift S star, such that x of b is equal to y of b in S star. Which just means, if you have some node b, then its x string is exactly equal to sum of its y strings for some shift. OK? That's very useful, because by a very simple observation, we can assume that there are only O tilde of k non-matching nodes in the tree. Right? If you think about it for a second, this is really the insight. Consider any optimal alignment between your 2 strings. There's some substitutions, some deletions, some insertions, whatever. But consider any node in the tree, let's say this one, for which its substring in x is not affected by any of the edits. Well, then clearly that one substring must match perfectly to some substring in y. And since we have only k edits, or at least we can assume that there's only those k edits, otherwise we're trivially in the far case, we can assume that on every level, on every layer of the tree, there's at most k non-matching nodes, meaning k times the depth, or k root log n many non-matching nodes as well. OK, good. So I said our goal was to reduce the number of non-trivial nodes in the tree to poly k, which in particular means, well, there's only poly k non-matching nodes. All I want to focus on in the next slides is on the matching nodes. We have to reduce the number of matching nodes also to poly k. OK. And so here's a second insight, or a definition rather. Let me define for a string x the following measure of structure. It's called the p block periodicity. OK, denoted by bp sub p of x. This is the smallest number L, such that you can partition x into L substrings, all of which are p periodic. Right, meaning that there's like a period of length at most p, and this string is obtained by copying this period infinitely many times. Here's a picture. If you consider this string, I claim that you can chop it into these 5 pieces, all of which are 2 periodic, which means that the block periodicity, like the 2 block periodicity of x is at most 5. OK? Mm-hmm. Now this indeed gives you like a certain spectrum of structure, where you have 2 like extremes. On the one hand, the block periodicity could be 1, which just means your entire string is periodic. Like you use very, very superstructured string. And at the other side of the extreme, the block periodicity can be as large as length of the string divided by p, which you can obtain by just chopping it into pieces of length p, which trivially are p periodic. This is what we consider a very aperiodic or a random-like string. OK. And now what we will do is we'll design special cases of our algorithm for all the nodes which are highly periodic and for all the nodes which are highly aperiodic. And then the intermediate case will just work. So let me start with the periodic case. So this picture should say the following thing. Focus on some node v in the tree. This is its substring x of v. This is like the entire substring of y, which is relevant for this node, which I called y of v before. And suppose on the one hand that this is matching. This is a matching node because we already said that only the matching nodes are the ones which we really care about. So there's this optimal shift S star such that the x string perfectly matches some y string. And let me also assume that this y string is highly periodic, meaning its block periodicity is 1, again, which just means this string is k-periodic. And, well, that just means there is a period, p, and you can just, you can express both y and x using a bunch of copies, possibly shifted of p. Okay, what's our goal in this entire thing? Remember from like the AKO algorithm, at every node what we want to compute is, we want to compute the edit distance of x to all the shifts of y. So what I'm just going to tell you is, actually these edit distances have a very, very simple form. They all look like this, okay? The only reasonable alignment from x to any string of y is you delete stuff in the beginning until your periods match, and then you follow these periods. That's exactly this form here. Actually, I also have a picture. Like this function, for like as a function of the shifts, it looks like this zigzag. If you happen to align perfectly with a period, it's cost 0. Otherwise, you delete or insert some characters in the beginning and end until you match this period. Okay? Just as a very quick argument as to why this should be true, the upper bound is pretty clear, but also the lower bound is not too hard. If you assume that your string is pretty long, like if your string is pretty short, it might have, you might maybe be able to get away with a very cheap alignment without following the periods. But if you have at least k repetitions of a period, every non-aligned period is going to cost you at least 1. So after, the cost would be way too expensive. The string's long enough. What's a little bit more interesting is the aperiodic case. So again, same situation. Focus on a node v in the tree. This is the substring x. This is substring y. And this time we're going to assume that, still they're matching. But we assume that the string in y is highly aperiodic, has very, very large block periodicity. And I try to make it kind of obvious, it should look random. Then what happens? Then I claim we still have a very easy way to express the edit distance from x to the shifts in y. This time it looks like this, which as a picture is this V shape. So the only reasonable alignment here is you just go to the one reasonable match from x to y, which is S star. Any other shift does not make any sense. So you just delete characters in the beginning or insert until you match exactly with S star. Okay. We started at 10 past. We're at 5 minutes. Okay.
So
yeah.
Why couldn't it be that the bottom string has things that are almost, that it's not periodic, but it's just off by being periodic because of a few sporadic errors?
Okay, it depends on how many sporadic errors, right? If you say it's less than k, then we're going to get to that later. If you say that there's like a lot of k sporadic errors highly apart, also if block periodicity would be more than k, then I claim still that this is the right form. I can show you why in the next slide. I can give you like a very quick proof. It's just a picture. So if you don't get it, don't worry. Like after this, it's more understandable again. So this is the alignment graph between x and y, which if you remember from Tomasz' talk yesterday, it means like these edges cost 1 and these cost 0, 1, depending on whether you match. Let me ignore the edges. Okay. Recall that x perfectly wedges y of v and S star, which means there's a 0 cost alignment here. Also, suppose that there is an alignment between x and y of v and S star, which has cost strictly less than what I claimed in the last slide. Now, I want to show that this leads to a contradiction. And the first insight is this. Recall that, v start off with a distance of s minus S star. This alignment has cost strictly less than that. So we do not have enough money for this alignment to go all to the left and meet this other alignment. Mm-hmm. Right? These two alignments will not touch. But if these two alignments do not touch, let me draw the following regions. Like this is the costly steps in the other alignment. Let me draw regions always like around these. This means in all the regions where we do not have any edits, you have two 0 cost alignments between x and y and a shift of y. But this means y is periodic in that particular region. Actually, it's periodic with period length 4k or something like this, so it's not exactly accurate, but up to constants, it's correct. Which means that actually this is a periodic region, this is a periodic region, this is so, right? All of these are periodic, and in total you have at most k periodic regions, which would prove that the block periodicity is actually less than k. But we assume it's more, so confirmation. Okay, so that if you put all this together, this is the algorithm which you write in. Right? Focus on any node in the tree again, as before. We're going to do the following steps. We'll test whether V is matching. Let's suppose it is. Then we'll test whether it's periodic, so whether its block periodicity is 1. If it is, we can just report this answer from before. We don't have to do any recursive computation. We'll just immediately report this. Okay, suppose it isn't periodic, then maybe it's highly aperiodic. In this case, we can also report a trivial estimate. And if all of these tests fail, we'll just continue recursively as in the AKO algorithm. Okay? Now, you should at least be convinced that this is a correct algorithm. I'm going to argue that it's also fast. So, yeah, for the running time, as I said before, what we want to do is we want to bound the number of non-trivial nodes in this tree. If this is the root, then we've already said before, there's at most O tilde of k unmatched nodes. So if you consider, in the same way you can kind of say there's at most O tilde of k matched nodes which are matched for the first time. So yeah, for all of these, how many non-trivial children can you actually generate? So as soon as you pass the matching test, right, the first line, either you're periodic, in which case you're yourself, right? There's no child nodes at all. Or you're highly periodic, in which case you're also alone. So the only case in which you still survive and spawn child nodes is if, well, you have your block periodicity strictly between 1 and k. But now remember what happens, right? The AKO algorithm, it continues branching. It always splits further the strings further and further. And if at some point you happen to have a part in your partition which is periodic, the algorithm will kill it. Which means on every level of the partition which follows below this particular node, you will split the string into at most k parts which are not periodic, right? Assuming that the block periodicity initially was at most k. Which means that actually you will ever reach at most, well, per level at most k non-periodic nodes, so in total also at most O tilde of k non-periodic nodes. There's a slight subtlety here, which is because actually for the for this test we also need the strings to be large. Remember this was necessary for the periodic argument to work out. So actually you also get like k-squared nodes due to this overhead. But ignoring this, in any case, we can bound the number of nodes by poly k. And that's really what we want to do, right? So that's great. Running time is k cubed, that's the number of nodes, times k per node, which is k to the 4. Which is a little bit weird though, because that would be faster than the lower bound. So something is fishy here. Can you spot what's fishy?
Checking the equality.
Checking
Equality.
Checking equality, sure, yeah, exactly. Like the n over k is missing, exactly. But what am I claiming here, which is clear nonsense? Well, I'm claiming you can do all these tests. And obviously, we're still in a sublinear time setting. You cannot just test whether you're matching with shift S star, because you would have to kind of read the strings. So what we really want to do is we also have to implement sublinear time algorithms for these 3 conditions. Right, so a sublinear time algorithm which tests matching, which tests periodicity, and which tests highly aperiodicity. And it turns out all of these can indeed be implemented, and all of these have the running time of the form n over k plus k, where n is the length of the respective substring that you apply them to. And it's a little bit more complicated because actually you also have to combine these tests with the precision sampling from before for them to actually give accurate results. But if you put it together, then you actually get the running time of the form n over k plus k to the 4. Good. I'm going to go into 3 minutes overtime because of the last talk, and I feel I deserve it. So let me give you like some notes on how to get actually to n over k plus k squared. So yeah, I don't want to say much. Like one insight which was pretty cute, we thought, is that you can actually have a better structural understanding of the block periodicity, which gives you, like, as a pre-processing, a way to assume that the block periodicity of x and y are just at most k. For like in the algorithm before, you could only assume it somewhere in the tree out of the sum, but actually you can like assume it as a pre-processing. And the idea is that, well, if you define a k break of a substring as like a substring which starts at a multiple of k and is not k periodic, then it turns out that the block periodicity is roughly equal to the number of k breaks. So consider, for instance, the string. Its block periodicity is 3 because you can chop it into 3 periodic pieces. And if you consider the breaks is exactly all these substrings which like overlap between the periodic parts. So it's very natural to see that the block periodicity is roughly equal to the number of breaks. This helps a lot algorithmically in order to make sure that the block periodicity is small in the first place. And the second thing is, there was this issue that for periodic strings, you actually had to assume that they're pretty long, of length k squared. And now what we did is we made it faster for strings which are significantly smaller than k squared, which requires a structural insight and then an algorithm to solve this subtask, to approximate the edit distance of a string and all of its rotations in almost linear time, for which you can either use the Andoni-Onak algorithm from 2009, which gives a subpolynomial factor approximation though, or Tomasz Mukherjee and Barna's algorithm on dynamic approximate edit distance, which is also based on the AKO algorithm. And then you actually also get the polylogarithmic approximation factor. OK, 3 quick open questions. First of all, can you improve the running time to what would be matching the lower bound, n over k plus root n? That would be amazing. What would be even more amazing is to get something resembling like a constant gap in sublinear time, right? All of these algorithms still have subpolynomial, polylogarithmic approximation errors. Anything like maybe log n or constant would be really cool, but they would require really, really different algorithm, and in particular understanding Alexander Negev's algorithm to a degree where you can actually improve it. Third point is it would also be cool to get sublinear time algorithms to approximate the LCS of 2 strings. So the fastest thing, unless I'm missing something, is a near linear time approximation, almost linear time, almost constant effector approximation. Would be cool to get something sublinear. OK, that's it. Thanks. Any questions? Yes.
If I would give you actually identity values for free, or for constant.
Sorry, can you say again? What?
If I would give you identity values for constants, for constant, checking equality of 2 strings just costs 2 constant.
Ah, okay.
But actually, do you still get a slower bound?
So you mean you allow me to test whether I can query an interval I to j, and you're going to tell me whether x of that interval and y of that interval are the same?
Right.
That's an interesting question.
Can you give an example which in k squared log n time? Because there's the equation of binary set on top of it.
Wait, but k squared log n, you said?
Yes. That's it.
Oh, yeah, exactly.
We can break the first part of the lower bound.
Yes.
The second part we don't know.
Yes, exactly.
Oh, I see.
That makes sense. Any more questions? Yes?
Right, so have you tried to prove a lower bound for constant gap?
No. All of these lower bounds they don't really care about the gap. They also work for subpolynomial or whatever. I'm not aware of anything specific for constant gap.
But maybe computational lower bound?
But then, how would you be able to distinguish constant from subpolynomial? I think, at least, I'm not aware of any technique which would have such a distinction. All these lower bounds, the n over k is just the lower bound that for Hamming distance, exactly, and that doesn't care about constant or subpolynomial, right? Yeah, would be interesting, of course.
Okay, so let's continue any further discussions over lunch. Thanks, Nick.